Up to this point in this class, we've learned all about chemical changes. We've learned about the individual structure of every single atom on the periodic table and what makes them unique. We learned about a particular pattern that we could create if we put them all in order of their atomic number or their number of protons. What we get, of course, is called the periodic table of the elements. We've learned about the patterns and the trends within that periodic table. And we've also learned quite a bit about how they bond with each other, the atoms, that is. What we're going to do now is talk about chemical equations. Chemical equations are a way to put on paper what a reaction is doing. So a chemical reaction, of course, is going to be creating something new that wasn't there before. Remember, the signs of a chemical reaction, of course, are the production of heat, the production of light, some sort of unexpected color change, a change in smell, or of course, bubbles are created, right? Those are all changes that a chemical reaction is occurring. Now, to put that on paper is a little bit difficult, but that's what we're going to be doing. We'll be talking about chemical reactions on paper, and we're going to learn how these actual elements react to each other to make new substances. So the first thing first is what we're going to talk about is a chemical equation, which is basically just a written form. Wow, let's try that again. A written form of a reaction. Again, we're taking like a real actual reaction happening at the atomic level, and we're trying to translate it and put it on paper. So that's what we call a chemical equation. All right, the symbols we're going to use in these chemical equations, the first one we're going to have right here stands for yields. Okay, so we're going to say the reactants are going to yield the products. The reactants, of course, are everything on the left side of the arrow. They're going to produce the products on the right side of the arrow. So we would say these plus this yields these products. So that the arrow literally represents the reaction. Okay, MnO2 in this particular example is something that is necessary for the reaction to occur. So for example, in the presence of manganese oxide, manganese 2 oxide, this reaction can go forward. It would yield the products. Without the manganese manganese 2 oxide, these would not, the reaction would not happen. If you see a delta sign, that technically means change, but what we're going to be talking about is some sort of heat produced. So some sort of heat produced in the reaction. The next one, a italics S stands for solid. So if you see a compound, for example, if I had H2O with a italicized S in parentheses after, that would basically be ice. That would be the liquid form of, or the solid form, excuse me, of water. Here we have liquid. Sorry, I was thinking ahead. Gas. So of course, if I had H2O with a G, that means it'd be water vapor. What we have right here is aqueous. Aqueous means that it's in water. Literally means it is in water. So an aqueous solution is dissolved in water. That's not the same thing as a liquid. A liquid, again, is something that is in a liquid state. But we could also put something else in water, and that would be an aqueous state or an aqueous solution, okay? Liquid and aqueous are not the same thing. All right, a chemical reaction is going to tell us three things that's very important. It's going to tell us what the reactants are. And again, the reactants are what are going into the reaction. Excuse me, I'm talking and I'm writing, and therefore I'm messing up. Reactants. Okay, let me, oh my gosh. Sorry, guys. There we go. Stop and think for a second. What the reactants are, and the reactants, of course, are going, the compounds that are going into the reaction, they're going to be acted upon, right? On the right side of the arrow, after the arrow, we're going to say what the products are. Again, the products are produced, so their products are always on the right side of a chemical reaction. They are produced by the chemical reaction on the reactants. And finally, the third thing it's going to tell you is going to tell us a ratio of all compounds in the reaction. Okay, so we're going to know how much of each of the reactants are present, how much of each of the products are present, and it's that ratio that's going to be given to us, and I'll show you guys that here in a little bit. Okay. The last thing I want to go over is the 7 diatomic elements. Now, diatomic may sound kind of intimidating, but really remember, di just means 2. So it's the 7 elements that when they are in the pure form, they are always buddied up by themselves in pairs. These are all, almost all gases. We have bromine, we have iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So if you see Br, it's going to be Br2. No, that's not a gas, but iodine, I2, nitrogen is called N2, chlorine is Cl2, HO2, O2, and F2, right? An easy way to remember this is a very silly word that has absolutely no meaning, but it sounds funny, and therefore it's very easy to remember, and that is Brinkelhoff. I always thought that, if you're going to be like a bad person in a movie, a science movie, say, instead of Heisenberg for Breaking Bad, Heisenberg could have been Brinkelhoff. I don't know. Anyway, Brinkelhoff is these 7 elements. The order doesn't make any difference, but Brinkelhoff is just an easy way to remember it. Some people prefer Hofbrinkel, but it's up to you, whichever one works for you. But those are the 7 elements that are always found in pairs when they are in the pure form. Now, if they're in a compound, obviously that ratio can change. I'm talking about if they are all by themselves.